Okay, so yesterday we left off the elevator questions, right? And we saw that the bungee jumper was still an example of an elevator because we had gravity acting down and an upward force working antagonistically with it, okay? And so as a result, we get either an acceleration that is straight up or straight down, okay, simple colinear vector type situation. Okay. For question number 2 here, okay, it's asking about during the bungee jump, the velocity of the 55-kilogram woman at the lowest point is 0. Because as you fall and the bungee cord takes up, okay, it stretches and it starts exerting a force upwards. In fact, the more it stretches, the harder it pulls. So you very quickly accelerate to a stop, okay, at the lowest point. Hopefully that lowest point is still somewhat above the ground. Okay. And at that point, yes, your velocity is 0. Okay, everyone with me on that part of it? Okay, so for part A, it says compare the direction of her acceleration at the lowest point of the jump to the part where she is accelerating due to gravity. So they're asking, when she first jumps off the bridge, okay, her acceleration is obviously which way? Down. But at the lowest point in her jump, which way is she accelerating? Up. Okay? When we were doing this question yesterday, the question was actually asking about that lowest point. Okay? At the lowest point, it said the bungee cord was exerting a force, okay? So we'll say force bungee, okay, of 825 newtons. Okay? How much is gravity? Okay, remember Fg, okay, is m times g, and it was 55 times 9.81, which was 539.5 newtons. Mine's like a steel trap. It's just always closed. It's a terrible dad joke. Okay, so we have 539 newtons down. We have 825 newtons up. Which way is the net force? Which way, guys? Up. Okay? If the net force is up, which way is she accelerating? Up. Okay? She's been accelerating up for how long? When did her acceleration cease to be down? Any ideas? When did her acceleration cease to be down? When she was falling, the bungee cord wasn't taken up, so it was slack. Couldn't exert any force. She starts to accelerate up as soon as the force in the bungee cord is greater than gravity, okay, which wouldn't be very long. Once that bungee cord starts to take up, okay, you now have an opposing force upwards. Okay? Even a small stretch in that bungee cord is going to produce a force upwards that's greater than gravity. Okay? That's the whole idea behind a bungee jump, is that you get a force that is upwards. Okay? It doesn't matter that she's moving downwards. She's accelerating upwards. That's why she slows down. That's why she doesn't hit the ground. Okay? Does that sort of make sense? Okay? We kind of forget about that, but a bungee cord is really the opposite of throwing something up in the air, which is also an elevator. Okay? If I throw something up in the air, as soon as it leaves my hand, it's actually accelerating down. It might be moving up, but it's accelerating down. The bungee jumper is just taking that and flipping it the other way. Okay? She's moving down, but she's accelerating up. That's why she stops. It's why something thrown up in the air stops. Okay? At its highest point. Here she stops at her lowest point. It's just the opposite of what we were doing before. Does that sort of make sense to everybody? Okay? All right. Here's the next type of Newton's second law question. So we've done the elevators. Okay, elevators just involve a vertical force and the force of gravity. All right. Now we're going to look at systems. Okay. A system involves more than one mass. Okay. That makes it sound like systems are really hard, but I'm going to show you that actually systems are almost exactly the same. Okay. So what I want you to do is copy this example down right now with the diagram. Okay, so we can walk through the forces involved in this system. This is where the identification of forces becomes really important, okay, where it can start to get kind of involved. Okay, so things we need to understand about a system. First thing is the thing I already said. A system is going to involve more than one mass. Okay, so in this situation we have a small block attached to a larger block by ropes. Okay, so there's a hand that is applying a force to the rope that's attached to the first mass. And then the first mass is attached by a rope to the second mass. Okay, so if I pull, so I've got this set up here that's basically the same. If you can't see it, stand up or come a little bit closer. Okay, when I pull on this string, I'm only pulling directly on the first mass. Would you agree? Do both masses move? Do they move at the same rate? They have to, because they're attached. Yeah, right? If I pull on the first one and it accelerates faster than the second one, what will happen? Will they stay attached? They would have to break apart. Then they would no longer be a system. Okay? Similarly, the back one cannot accelerate at a greater rate than the front one, or it will pass it or catch up to it. Okay? Does that happen? Like when I pull on the front block, all I see is the blocks moving in the same way because they're part of the system. All parts of the system have to have the same acceleration. That is the key characteristic of a system. You might want to write that down somewhere. Okay? In any system, all the parts have the same acceleration. Okay, I've taken all the masses out of that back block. Now the blocks have different masses. If I pull on the front block, is it going to change anything? It'll actually change one or two things. Is it going to change the acceleration? Well, it could because I'm pulling on less mass, but let's just say when I pull this, do they still move with the same acceleration? Like they each have the same acceleration. Okay, so that's still true. It doesn't matter what the masses are. All the parts of that system, all the masses in the system are going to have the same acceleration. But the forces might change. Okay, now that that second block is lighter, is there going to be less force in this string that connects the two? There has to be, otherwise its acceleration would be different than the front one. Okay, so yes, changing the mass can change the forces involved. Okay, but it can't change the acceleration of the system. Okay, the system has an acceleration. The parts of the system have that same acceleration, regardless of their mass. Okay, so let's look at this problem here. So we've got these two blocks. They're like these ones. They're identical, made of identical material. Okay, so that means that the way they interact with the surface is the same. Keeps friction essentially similar. Okay, they're connected by a light rope on a level surface, and an applied force of 55 newtons to the right causes the blocks, plural, to accelerate. Okay, so I know in this situation that there is a force of 55 newtons forwards. Okay, while in motion, the magnitude of the force of friction on the block system is 44.1. So which block do I apply that to? Both. It says it applies to the block system. Can I simplify this diagram then? Can I make this diagram look like this? I can. Now, when I calculate the acceleration of the system, I'll get the same number for both blocks because I'm calculating it for the whole system. Okay? That's the thing we have to remember about systems. All parts of the system have the same acceleration, or at least in magnitude. If you have a pulley, you can actually change the direction they accelerate, but they would still have the same magnitude of acceleration. Okay? So, can I calculate the net force? I sure can, right? I got 55 forward, 44.1. It's level, so gravity and normal force cancel each other out. Okay, so I'm looking at 10.9 newtons, right, as a net force. Okay, F net is 55 minus 44.1. Okay, so pretty sure that's 10.9, right? Let's double check. My math hasn't been good today. Okay, so 10.9 newtons forward. All right, can I calculate the acceleration now?
Could be forward or right.
Oh, did it say right in the question? Said right, yes, sorry, absolutely, it should be right. Right, it should be right. Okay, can I calculate the acceleration? Okay. Can I do this? Like we learned yesterday? Okay. I know the net force, I know the mass, right? I can calculate the acceleration of the whole system, which would then also be the acceleration of the individual blocks. Okay, so F net over mass will equal acceleration, so 10.9 divided by 30 kilograms. So 0.36 meters per second squared. Right. Okay. Now, here's how I would ask that question. I'd write everything exactly the same except the last sentence. I would say, calculate the acceleration of the 10 kilogram block. What would you do different? Nothing. Okay? I don't know how much that rope that's connecting the two boxes is pulling on the 10 kilogram mass. I don't know how much of that 44.1 newtons worth of friction is acting only on the 10 kilogram mass. It doesn't matter. Every part of that system has the same acceleration. So if I can find the acceleration of any part or the whole system, I can apply it to everything. Okay? So I wouldn't actually have to do anything different. But if I ask it that way, you'd be surprised how many people change this calculation right here to 10.9 divided by 10. As soon as I mention which mass, suddenly people forget in a system, I'm talking about the whole system, not just one part of it. Okay? Everyone follow me there? Okay. Now this is where this system will start to get involved. We just dealt with basically the same kind of question we were doing yesterday. Here's a mass, it's being pulled forward, it's being pulled backward, find the net force, calculate the acceleration. Okay? Building on this, now we go to calculate the tension in the cable, or in the rope that connects the two boxes. Okay? They have to give you one more piece of information to do that, okay? But it's going to be possible. So, try number 2. That's the next thing here, okay, is calculating the tension in this rope if the force of friction on the 10 kilogram block is 14.7 newtons. Okay, so they gave you one more piece of information. Okay, this force here is still 55 newtons. The combined frictional force is still 44.1, but now we know that 14.7 of that 44.1 is on the first block, is on the 10 kilogram block. Okay, so we want to find how much force there is in that rope that is connecting the blocks. There are 2 ways to do it. Both will arrive at the same answer. Here's what you need to think about when you're approaching this. That rope is doing 2 things. it is pulling forwards on the 20 kilogram mass, but it is pulling backwards on the 10 kilogram mass. Okay? So the two ways you can do this is you can solve it with the big mass or the small mass. Okay? Here's the other thing you need to know. You already calculated this number, and it still applies. And it applies to both blocks. This is where it gets tricky. This is where things get interesting. I'm going to give you guys a few minutes to think about that. All right, so as I was saying, the first step is pick a box and then draw the free body diagram for that box. The easiest box to do this for is probably the first box because we have a bit more information about it. Okay? It'll be like one less step. All right, so I'm going to draw the 10 kilogram box here. Okay, how many forces are acting on the 10 kilogram box? Okay, horizontal forces. 3. There are 3 horizontal forces acting on the first box. Okay, that's going to, and seeing from your face is like, well, there you're going crazy. It's like friction and the force pulling it. That's only 2. What's the other force? What's attached to the 10 kilogram box? A rope, which is attached to a 20 kilogram box. What's easier, walking like this or being attached to a wagon full of cinder blocks and trying to do the same thing? Way easier to walk when you're by yourself, right? Pulling a wagon full of cinder blocks is a lot more mass. Does that mass resist you? Because it has mass, it has inertia. Okay? You're not just changing your inertia, your velocity, you're also changing the velocity of the cinder blocks on the wagon. That's the same situation here. Okay? It's why you don't tow a 30-foot fifth-wheel trailer with a Honda Civic. Well, in addition to the fact the mechanics of that are mind-boggling. But okay, you wouldn't be able to pull a big giant trailer with something so small because it can't exert enough force to move all that extra mass. Okay? So the 3 forces are the force of friction, which we were told is 14.7 newtons. The tension in the rope, which is the force, incidentally, we're being asked to find in this question, and the applied force of 55 newtons. Okay? Those are the 3 forces. And I'm being asked to find this one. Okay. Do I know the mass of the block and the acceleration of the block? What can I find with those 2 numbers? Force net, right? Force net equals mass times acceleration. Okay? So in a system, I can actually deal with the whole system, or I can break it up into its individual parts and deal with the parts individually. As long as I understand all the parts have the same acceleration, I'm good. Okay? So I can calculate F net because the 10 kilogram block has a mass of 10 kilograms, and it has an acceleration of 0.36 meters per second squared, because that's the acceleration of the whole system. That means that my net force is 3.6 newtons to the right. Is everyone okay with that? Okay, what's the other way to calculate net force? The vector sum of all forces. For the 10 kilogram block, that means F net equals force of friction, which I know, plus applied force, which I know, plus the force tension, which is the one they want me to find. Do I know 3 out of those 4? I do. Now I can find the missing force. All I have to do is subtract off the ones that I know. All right, so I'm going to have F net minus the force of friction minus the applied force equals the only other force that's acting, the tension in the rope that's connecting the two boxes. Okay, so when I plug that in, I'm going to have 3.6 newtons right minus 14.7 newtons left, so minus negative, okay, minus 55 newtons, the force forwards. Okay. If I do that, I should get like 36 point something, right? So 3.6 minus negative 14.7 minus 55. 36.7 newtons. Okay. So, and it came out on my calculator negative, which means it's backwards. Is that the direction that that rope should be pulling on the 10 kilogram mass? Should be pulling backwards, right? Okay. So the tension in that rope is 37 newtons left. Okay, everyone all right with that? Now, here's the other way I can solve for that. I can use the 20 kilogram mass. Okay, the 20 kilogram mass only has how many horizontal forces acting on it? 2. Okay, the 20 kilogram mass is only being pulled forwards by the force we're supposed to find and backwards by friction. Okay, do they tell me how much friction is acting on the back box? They don't. But they told me the total amount of friction in the whole system and how much of it was on the first block. So can I find how much of it's on the second block? Just have to subtract those numbers, right? So if I'm looking at the second box, okay, 20 kilograms. There's the force I'm supposed to find, the tension in the rope connecting the two boxes, okay? And the force of friction acting backwards, which is going to be 44.1. That was the total friction, minus 14.7. That's how much of it was on the second block, or the first block. So 29.4 newtons worth of friction on the back block. Okay. I know the mass of that block. Do I know the acceleration of that block? Can I find the net force on that block? Absolutely. Okay, 20 times 0.36. Okay, so I get 7.2 newtons. And that'll be right. Okay, so 7.2 newtons to the right is the net force. What's the other way to calculate net force? M times A and the vector sum of all forces. So on this box, I only have these two forces. So F net, which I know because I just calculated it, equals force of friction, which I know because I calculated it here, plus the force in the rope. So if I subtract the force of friction over, that should leave me with that force that's pulling forwards via the rope. Okay, so when I plug in my numbers, I'm going to have 7.2, my net force going to the right, minus negative 29.4, that's my friction, which is acting to the left. Okay, that's going to give me the force of tension. Just looking at that, is that going to be 36.7? Pretty sure it is. Okay. Is that exactly the same number I got with the other box? Well, the two significant digits is only 37, but it's the same number I got, which is good. I should get the same number. It's the same rope. Okay? You can't be pulling harder on one than the other. Okay? You see how this can get involved in a hurry? Was there any really challenging math in that, though? I had to multiply mass by acceleration. I had to add and subtract. That's it. Okay? That's what's tricky about Unit 2. The math in Unit 2 isn't very hard. It's getting to the math that's tricky. It's being able to look at this situation, break things apart and go, which forces are there? What are they doing? Okay? How do I understand what these forces are going to do? How are they going to affect that mass? That's the tricky part. There is a lot of intuitive leaps that have to be made in any Newton's second law problem before you can even get to the math, which, unless you've got any trig in it, is going to be multiply, divide, add, subtract. Okay? Like, it's not going to be complex math by any stretch. Okay? All right, questions on that one? That's tricky. Okay? Again, not mathematically tricky, but contextually tricky, intuitively tricky. All right. Try number 1. It's kind of an elevator. Kind of. But it's also a system. Okay, so we have 2 buckets of nails, one hung above the other, pulled up by a roof, or to a roof by a rope. Each bucket has a mass of 5 kilograms. The tension in the rope connecting the buckets is 60 newtons. Calculate the acceleration of the buckets. Okay. Is that the situation we have? Right? 2 buckets connected by a rope. All right? All I know is that the tension in this rope is 60 newtons. What other force is acting on that bottom bucket? Gravity. Can I calculate that? Okay. So, so I've got 49.05 newtons of gravity acting on the bottom bucket, okay? 60 newtons acting up on the bottom bucket. I know nothing about the top bucket except there's 60 newtons acting down plus the force of gravity on that bucket. Okay, would you agree? Which bucket should I use to calculate for this question? The bottom one or the top one? The bottom one. I know way more about the bottom one. And it's way easier to deal with that one than the top one. Okay? Plus, I have no idea what this force is. They never told me that. Basically impossible to use the top one. Right? So, I want to find the acceleration of the buckets. Well, if I calculate the acceleration of this bucket, that's also the acceleration of that bucket and the bucket system. All of them. That's what I have to remember about a system. Any one part of it has the same acceleration as any other part of it. All right, so I'm going to forget about that bucket, and I'm just going to deal with this one. Can I calculate the net force on this bucket? Vector sum of all forces, right? 60 newtons up, 49.05 newtons down. Okay, tells me the net force on this bucket, 60 minus 49.05 gives me 10.95 newtons. Okay, that's the net force acting on the bottom bucket. Can I find the acceleration of the bottom bucket? Okay. Okay, so 10.95 divided by, I'm only dealing with the bottom bucket here, so only the mass of the bottom bucket for this one, because that's the only part of it I'm dealing with, gives me 2.2 meters per second squared up. How much math was there in that one? Like 3 steps, right? I had to calculate the force of gravity by going m times g. I had to calculate the net force by subtracting 2 numbers, and then I had to divide 2 numbers to get the acceleration. Okay? Was there a lot of figuring in that question? Okay, you're gonna hear me say this like until you get sick of it, but in this unit, that's what the questions are like. Okay, even in physics 30, okay, this is what the questions are like. You gotta think about the physics. It's not about the math. That's why I can do physics. I'm not terribly good at math, okay, but I can think about physics. And that's what's more important. Okay. Your math teachers would disagree, but they're wrong. Thinking about physics is more important. Okay, is this still a system? Okay, it is. Pulleys are prime examples of systems. Okay. What force is going to drive this system? Gravity. Okay, those two masses are not equal. So if I let that go, if I'm holding those two masses and I just suddenly let them go, which that would be interesting, me holding these, because this is like 75 pounds and this is like 50 pounds. Okay, but yeah, if I'm just holding those two things and I let them go, it's going to do this, right? The 35 kilogram mass is going to fall and the 25 kilogram mass is going to lift, okay? Because that pulley is essentially a lever, okay? It's changing the direction of the force. While this one's going to go down and this one's going to go up, is the rate at which they go up and down going to be the same? Yes. They're connected by a rope. They have to accelerate at the same rate. Which means, as complex as this diagram looks, all it really is this. A 60 kilogram mass being pulled in two different directions. Okay. Is there 60 kilograms worth of mass in that system? There is. Okay. And it's being pulled by gravity, but because of the pulley, gravity makes it look like it's working, well, it is working against itself. Okay. On this side here, I'd have the force of gravity on the 35 kilogram mass, which would be 343.35. Okay. And on this side, I would have the force of gravity on the 25 kilogram mass. Okay. Can I calculate the net force? Would I then be able to calculate the acceleration? Okay. Again, there's not a lot of calculating to do in this question. But arriving at the idea that this is really one mass being pulled in two different directions is the challenging part. Right? Being able to look at this situation and go, what's going to happen here? Why is it going to happen like that? Now I got to calculate some numbers. Okay? When it comes right down to it, you can do what I did here with any system. All the masses move together and they move at the same rate. So I can combine them into one big mass, if it fits. It didn't fit to do that with the buckets of nails. It was easier to isolate the parts and deal with an individual part, and then apply it to the whole. In some questions, it's more appropriate to deal with the whole, and then apply it to the little parts. Right? But again, you have to figure out which one is going to be appropriate for the question you're dealing with. Okay? That's why we spend so much time on Newton's second law. Not because we got to work on the math, it's because we have to work on the physics. Okay? We have to be able to identify all this stuff within a given situation. Okay, now here's the trick with this question. Once I calculate the net force, which is going to incidentally be 98.1, okay, F net's going to be 343.35 minus 245.25, and it's going to be 98.1 newtons. Okay. When I calculate the acceleration, that's going to be F net divided by m, so 98.1 divided by 60. Oh shoot, started that up again. So 1.6 Okay. What's missing from my answer? Okay, direction. Here's how this gets weird with what we're doing. Okay, the question asks, describe the motion of each object once the objects are released. Well, each object is going to accelerate at 1.6 meters per second squared. One of them is going to be down and the other is going to be up. Now, what if the question asked, what's the acceleration of the system? Then what do I say? I don't give a direction. That question could never ask me, what's the acceleration of the system? It could ask me, what's the acceleration of the system's magnitude? That's all it could ask for. I can't give a direction for the whole system because the parts of the system are going in different directions. So I can isolate it. I can say, if it asks, what's the acceleration of the 25 kilogram mass? I can say 1.6 meters per second squared up. Okay? But if it asks for the whole system, it can only ask for the magnitude because they don't go the same direction. So all I could put would be 1.6 meters per second squared. Yeah. Okay? Everybody all right with that? He's getting hairier. They are. And this is day 3 of 10. Okay? So they're going to get even hairier. We haven't even started doing any vectors yet. Okay? Okay, in your digital workbook here, guys, so you're gonna have to go to the dynamics one now. Okay, we're done with the kinematics one, so. Okay, I would like you guys, we'll give you some easy ones here, get your confidence back after I've overwhelmed you a little bit here. Right, I would like you guys to try for the remainder of class here 1 through 7. They're much, much more basic. You have to really some acceleration stuff and some F times A equals M times A stuff. Okay, like much, much simpler than what we just did. Okay, so this is on like page 2 of your digital workbook, so let me working from there. I'll blow it up a little bit bigger here.